To familiarize ourselves with the new and the old vocabulary of mole concept, in this video, let us try to solve some very basic examples in mole concept. And let us start with the definition of the latest standard or reference used for measuring masses of atoms, molecules, subatomic particles, ions, and so on. The latest reference for measuring the masses of such particles is unified atomic mass unit, and by definition, one unified atomic mass unit is 1/12 of the mass of an atom of C12 isotope. And the symbol for unified atomic mass unit is small u, and the value of one unified atomic mass unit in kilograms is approximately 1.66 times 10 to the power of minus 27. And in honor of John Dalton, one unified atomic mass unit is also known as 1 Dalton, and the symbol for Dalton is Da. So, using mass spectrometers, we experimentally measure the masses of atoms, molecules, ions, subatomic particles using unified atomic mass unit as the standard or the reference. That is, in comparison to 1/12 of the mass of an atom of C12 isotope. And for atoms, John Dalton defined something known as atomic weight. It is by definition the ratio between the mass of one atom of the element and mass of some reference or standard that is used to measure the masses of atoms. And you know the latest reference is one unified atomic mass unit, or this. So that is why we have this in the denominator here. So by definition, atomic weight is the ratio between these two masses. Because we have the same physical quantity mass both in the numerator and the denominator, we will have the same dimensions both in the numerator and the denominator, and they get cancelled. Therefore, atomic weight is a dimensionless number. And we can measure experimentally using mass spectrometers the atomic weights of different elements using unified atomic mass unit as the standard. And we have a new name for atomic weight, that is relative atomic mass. So remember, atomic weight and relative atomic mass are one and the same. Atomic weight was the original name given to this ratio by John Dalton, whereas relative atomic mass is the new name for the same ratio. So these two are one and the same. Now if you take the example of sodium, the atomic weight of sodium is approximately 23. This is the experimentally measured atomic weight of sodium. Now what does this number tell us? This number tells that one atom of sodium is approximately 23 times as heavier as the standard, that is one unified atomic mass unit, or this. And remember, atomic weight is just a number, so it is 23 without any unit next to it. Now the question is, what is the atomic mass of sodium? Remember, atomic mass is the mass of one atom of the element. So atomic mass of sodium is the mass of one sodium atom. It represents the physical quantity called mass. So it must be expressed in some units of mass. And if you look at this ratio, that is what we have in the numerator here, atomic mass or mass of one atom of an element. So if you want to get the atomic mass, because we already know the atomic weight, all you have to do is multiply atomic weight with whatever we have in the denominator here. What we have in the denominator here is 1U. So to get the atomic mass or mass of one atom of an element, you have to find out the experimentally measured atomic weight and simply multiply it with 1U. So in case of sodium, it is 23 multiplied with 1U, that is 23U. So the atomic mass of sodium is 23U. Remember, here U is a unit of mass. So this represents the physical quantity mass. Whereas atomic weight has no units, it is just a number. So it does not represent the physical quantity mass. So notice the difference between these two. Now if you want to express the mass of one sodium atom or atomic mass of sodium in kilograms, you can do that. You know that 1U is approximately equal to these many kilograms. So to get the mass of one sodium atom in kilograms or atomic mass of sodium in kilograms, you simply replace 1U with this value. So it would be 23 times 1.66 times 10 to the power of minus 27 kilograms. So this is the atomic mass of sodium in kilograms. This is the atomic mass of sodium in unified atomic mass units. This U and this kg both are units of mass, but the difference is kilogram is an SI unit of mass, whereas unified atomic mass unit is a non-SI unit of mass. But we can measure the masses of atoms more accurately using mass spectrometers in unified atomic mass units. That is why we use this unit to express the atomic masses of atoms. And of course, for whatever reason you want the mass of the atom in kilograms, you know how to do that. Now the next question is, what is the molar mass of sodium? See, molar mass of any substance by definition is the mass of the substance per 1 mole of that substance. And you know, 1 mole of any substance contains an Avogadro's number of particles. Now, what do we mean by particles in case of sodium? You know, sodium is a metal and all metals are monoatomic. That means their molecules contain only one atom each. Or in other words, they are only composed of atoms and they do not contain molecules. So, for sodium, by particles we mean atoms. So 1 mole of sodium contains an Avogadro's number of sodium atoms. And you know, the experimentally measured value of Avogadro's number is approximately 6.022 times 10 to the power of 23. This is the value of Avogadro's number. Now you may be wondering why we picked such weird looking number for the value of Avogadro's number. Why not a nice round figure? The reason being, if you take this number for the value of Avogadro's number, then the molar mass of those particles will be numerically equal to the relative mass of those particles. So in case of sodium, the molar mass of sodium atoms will numerically be equal to its atomic weight, that is 23. And because it is the ratio between mass and the amount of substance, it will have the unit gram per mole. So we picked this particular value for Avogadro's number for this convenience. So the molar mass of sodium is simply equal to its atomic weight expressed in grams per mole, because sodium is composed of sodium atoms. It is its atomic weight expressed in grams per mole. So what is the molar mass of sodium? It is 23 grams per mole. Now what is 1 gram atom of sodium? Remember, gram atom is a shorter name for gram atomic weight. Gram atom and gram atomic weight are one and the same, and they are old vocabulary. And by definition, 1 gram atom of any element represents certain mass of the element that is equal to its atomic weight in grams. Because the atomic weight of sodium is approximately 23, 1 gram atom of sodium is approximately 23 grams. As simple as that. And you know, 1 gram atom of any element contains an Avogadro's number of atoms. We have proved this in some other video. So the molar mass of any substance is its mass per 1 mole of that substance, and 1 mole of any substance by definition contains an Avogadro's number of particles, and in case of sodium they are atoms. And the unit for molar mass is grams per mole. So the molar mass of sodium is 23 grams per mole, whereas 1 gram atom of sodium is 23 grams. Now the atomic weight or the relative atomic mass of copper is 63.54 approximately. Then the atomic mass of copper is simply 63.54 U. That is the mass of 1 copper atom in unified atomic mass units. And if you want its value in kilograms, it would be 63.54 times. See, you have to replace 1 U with its value in kilograms, and that is 1.66 times 10 to the power of minus 27 kilograms. Then what is the molar mass of copper? Remember, molar mass is the mass of the substance per 1 mole of the substance, and 1 mole of any substance contains an Avogadro's number of particles. Because copper is also a metal, the particles that copper is composed of are copper atoms. So it is its atomic weight, that is 63.54 expressed in grams per mole. So 63.54 gram per mole is the molar mass of copper. Then what is 1 gram atomic weight or 1 gram atom of copper? It is by definition its atomic weight in grams. So it is simply 63.54 grams. Now here we have another example. The atomic weight or the relative atomic mass of oxygen is 16 approximately. Then the atomic mass of oxygen is simply 16 U, the mass of 1 oxygen atom in unified atomic mass units. And in kilograms it would be 16 times 1.66 times 10 to the power of minus 27 kilograms. Then what is the molar mass of oxygen? And this is a bit tricky, because molar mass is the mass per 1 mole of the substance, and 1 mole of any substance contains an Avogadro's number of particles. Now what do we mean by particles in case of oxygen? Oxygen under normal conditions is composed of oxygen molecules, and each oxygen molecule consists of 2 oxygen atoms. It is diatomic. But under some circumstances, oxygen is composed of oxygen atoms. So when you say oxygen particles, are we talking about oxygen molecules or oxygen atoms? So there is some confusion here. So to avoid that confusion, we have to clearly say the molar mass of oxygen when it is composed of atoms or molecules. So molar mass of oxygen atoms then would be its atomic weight, that is 16 in grams per mole. So the molar mass of oxygen atoms is 16 grams per mole. Then what is 1 gram atom of oxygen, or 1 gram atomic weight of oxygen? It is simply 16 grams of oxygen. So I believe now you understand how to figure out the atomic mass, molar mass, and the values of gram atoms of different elements that are composed of atoms. You know, all inert gases and all metals are monoatomic. They are composed of atoms, or their molecules contain only one atom each. Now there are many substances that are actually composed of molecules. A molecule is a stable group of atoms in which the atoms are bonded to one another. Now you know there are many elements like nitrogen, oxygen, fluorine, sulfur, phosphorus, etc. that are actually composed of molecules. Similarly, there are many compounds like water, carbon dioxide, methane, sugar, glucose, etc. that are also composed of molecules. Now, we can define something known as molecular weight for molecules just the way we defined atomic weight for atoms. And molecular weight by definition is the ratio between these two masses. This is similar to the definition of atomic weight. We just have to replace atom with molecule here. And again, this is a dimensionless number. And also we have a modern name for molecular weight that is known as relative molecular mass. Just the way atomic weight has the modern name relative atomic mass, molecular weight also has a new name called relative molecular mass. Now let us take the case of oxygen. Under normal conditions, oxygen is composed of oxygen molecules, and in each oxygen molecule there are 2 oxygen atoms, so its atomicity is 2. And you know the experimentally measured atomic weight of oxygen is approximately 16. Because one oxygen molecule is composed of 2 oxygen atoms, you have to multiply its atomic weight with its atomicity to get its molecular weight. So the molecular weight of oxygen is 32. Now this is again a number without any unit written next to it, and this number tells the number of times one molecule of oxygen is heavier than the standard that we chose. Now what is the molecular mass of oxygen? See, molecular mass is nothing but the mass of one molecule of the substance. So it represents the physical quantity called mass. So you have to express it in units of mass. So if you express it in unified atomic mass units, molecular mass is nothing but its molecular weight numerically. So the molecular mass of oxygen is simply 32U. And if you want to express it in kilograms, you know 1 U is equal to 1.66 times 10 to the power of minus 27 kilograms. So this will be the mass of one oxygen molecule in kilograms. Now the next question is, what is the molar mass of oxygen? See, molar mass is mass per 1 mole of the substance. Now 1 mole of any substance contains an Avogadro's number of particles, but in case of oxygen, what do we mean by particles? Here I am referring to oxygen molecules. So here I am looking for the molar mass of oxygen that is composed of oxygen molecules. So if you take 1 mole of oxygen that is composed of oxygen molecules, there will be an Avogadro's number of oxygen molecules in it. Then the molar mass will be simply equal to its molecular weight in grams per mole. As simple as that. So molar mass of oxygen molecules is simply 32 grams per mole. Now notice the difference here. Molar mass of oxygen atoms is 16 grams per mole. That is mass of oxygen per 1 mole of oxygen that is composed of oxygen atoms. Whereas this is molar mass of oxygen that is composed of molecules, mass per 1 mole of oxygen that is composed of oxygen molecules, so it will be 32 grams. Now the next question is, what is 1 gram molecular weight of oxygen? Again, gram molecular weight, gram molecule, gram mole and mole, all these are old vocabulary and they all mean the same. These are increasingly shorter versions of gram molecular weight. And by definition, gram molecular weight represents certain mass of the substance that is equal to its molecular weight in grams. So it is simply 32 grams. So 1 gram molecular weight or 1 gram molecule or 1 gram mole or simply 1 mole in the old sense of oxygen means 32 grams of oxygen. Now, what is the molecular weight of nitrogen? Again, the experimentally measured atomic weight of nitrogen is 14, and we know that nitrogen is diatomic. That is, a molecule of nitrogen contains 2 nitrogen atoms. So its atomicity is 2. If you multiply its atomicity with its atomic weight, you will get its molecular weight. So the molecular weight of nitrogen is 28, or its relative molecular mass is 28, just the number 28. Then what is the molecular mass of nitrogen? That is the mass of 1 molecule of nitrogen. It is 28 U. You simply have to add the unit U to it. And again, in kilograms, it would be 28 times 1.66 times 10 to the power of minus 27 kilograms. Then what is the molecular mass of nitrogen? Again, it is mass per 1 mole of nitrogen, and 1 mole of nitrogen, if it is composed of nitrogen molecules, contains an Avogadro's number of nitrogen molecules. Then the molar mass of nitrogen, when it is composed of molecules, would be its molecular weight in grams per mole. Then again, look at these 4 old terms. 1 gram molecular weight, gram molecule, gram mole and 1 mole in old sense of nitrogen is simply its molecular weight, that is 28 in grams. Now let me ask you, what is the molar mass of nitrogen when it is composed of nitrogen atoms? That is mass per 1 mole of nitrogen that is composed of nitrogen atoms. It would be its atomic weight, that is 14 in grams per mole. So pay attention to that. Now what do we have in the next example? We have the compound methane. CH4 is the experimentally determined molecular formula of methane. And each molecule of methane is composed of 1 carbon atom and 4 hydrogen atoms. And we know the atomic weights of carbon and hydrogen. The atomic weight of carbon is approximately 12 and that of hydrogen is approximately 1. And the subscript for carbon here is 1. So you have to multiply the atomic weight of carbon with its subscript, and the same with hydrogen. Multiply the atomic weight of hydrogen with its subscript and then add all these terms to get the molecular weight of methane, and it will be approximately 16 with no unit next to it. So one molecule of methane is approximately 16 times as heavier as our standard or reference, that is one unified atomic mass unit. Then what is the molecular mass of methane? That is the mass of a single molecule of methane. So you simply have to attach the unit U to it. So it will be 16U, or 16 times 1.66 times 10 to the power of minus 27 kilograms. Then what is the molar mass of methane? Again, it is the mass of methane per 1 mole of methane, and 1 mole of methane is composed of an Avogadro's number of particles. In case of compounds, we do not have the confusion that we had in case of nitrogen and oxygen, because compounds are always composed of molecules. So molar mass of methane is simply its molecular weight, that is 16 expressed in grams per mole. Again, look at these 4 old terms. It is nothing but 16 grams. So 1 mole in old sense, or 1 gram mole, 1 gram molecule, and 1 gram molecular weight of methane is simply 16 grams of methane. Now, in case of covalent compounds like methane, carbon dioxide, sulfur trioxide, fructose, and so on, the formula that we use to represent the compound also represents 1 molecule of that compound. So the formula of methane is CH4. What do we understand from this formula? We understand that methane is composed of separate independent methane molecules, and in each methane molecule there is 1 carbon atom and 4 hydrogen atoms. That's what we mean by this formula. That is why for molecular substances in general, the formula is also known as the molecular formula. But there are certain compounds like sodium chloride, potassium nitrate, potassium dichromate, and so on, that do not contain molecules. The idea of molecule is not applicable to ionic compounds. Then what do we have in ionic compounds? Ionic compounds are composed of a large number of oppositely charged ions in some arrangement. So there are no separate, independent, stable molecules in case of ionic compounds. Then how do we represent the formula of ionic compounds? Now, to represent the formula of an ionic compound, you have to write the symbols or the formulae of the ions present in that compound next to one another. Then represent the ratio of the ions in the simplest possible ratio. Now, experimentally we found that in sodium chloride, the ratio of sodium ions and chloride ions is 1:1. That is why we show them with the subscripts 1 each. That is why the formula of sodium chloride is NaCl. So what does this formula NaCl represent? Does it represent a molecule of sodium chloride? No. Sodium chloride is an ionic compound. You must know that. And there are no molecules in sodium chloride. Then what does this formula represent? It tells you the various ions present in that compound and the simplest ratio of those ions. So from these subscripts, you need to understand that they are in the ratio of 1:1. That is, they are present in equal number. So this formula of sodium chloride represents the smallest possible unit in the compound sodium chloride. That is why it is called its formula unit. Now, just the way we have defined molecular weight for molecules and atomic weight for atoms, we can define what is called as formula weight for formula units, that is for ionic compounds. And it is defined as the ratio between these two. And it also has the name relative formula mass. Again, formula weight or relative formula mass is a dimensionless number. It tells the number of times one formula unit of that ionic compound is heavier than the standard that we chose. Now let us take the example of sodium dichromate and find out its formula weight. We are given the atomic weights of sodium, chromium and oxygen. These are their approximate atomic weights. And from this formula, you understand that it is composed of 2 sodium ions and 1 dichromate ion. And in each dichromate ion, there are 2 chromium atoms and 7 oxygen atoms. So to get the formula weight of sodium dichromate, you have to multiply these subscripts with their respective atomic weights. So it would be 2 times 23 plus 2 times the atomic weight of chromium is approximately 52. So 2 times 52 plus 7 times 16. I will let you do the math to figure out the formula weight of sodium dichromate. And upon calculation, this comes to be around 262. So that is the formula weight or the relative formula mass of sodium dichromate. That means one formula unit of sodium dichromate is so many times heavier than our standard. Then what is the formula mass of sodium dichromate? I think now you know the drill. It is nothing but its formula weight in unified atomic mass units. So it will be 262 U, and in kilograms it would be 262 times 1.66 times 10 to the power of minus 27 kilograms. Then what is the molar mass of sodium dichromate? That is mass per 1 mole of the substance, and 1 mole of any substance contains an Avogadro's number of particles. Here by particles we mean the formula unit, that is Na2Cr2O7. So it will be simply equal to its formula weight in grams per mole. So that is the molar mass of sodium dichromate, simply its formula weight in these units. Then what is 1 gram formula weight of sodium dichromate? Again, it is simply its formula weight expressed in grams. Remember, this is old vocabulary. So that is about formula weight in case of ionic compounds. And for ions, we can define something known as ionic weight, just the way we have defined formula weight, molecular weight and atomic weight. And ionic weight is also known as relative ionic mass. And you know, by definition, it is the ratio between these two. Again, it is a dimensionless number. Let us calculate the ionic weight of sulfate ion. This is the formula of sulfate ion. It is composed of 1 sulfur atom and 4 oxygen atoms. And for all practical purposes, you can ignore this negative charge present on the sulfate ion while calculating its ionic weight. And the atomic weight of sulfur is approximately 32, and the subscript of sulfur here is 1. So you multiply the atomic weight of sulfur with its subscript plus the atomic weight of oxygen is approximately 16 and its subscript is 4. So 16 times 4. So that becomes 32 plus 64. Is it 96? Yes. That is the ionic weight of sulfate ion. That is, 1 sulfate ion is approximately 96 times as heavier as our standard or reference. Then what is the ionic mass of sulfate ion? That is the mass of a single sulfate ion, and you know the drill. It is simply its ionic weight expressed in unified atomic mass units, 96U, or in kilograms it is 96 multiplied with 1.66 times 10 to the power of minus 27. And what is the molar mass of sulfate ions? Again, you know the drill. It is simply its ionic weight in grams per mole. Then what is 1 gram ionic weight, also known as 1 gram ion? Remember, this is again old vocabulary, and you also know how to figure this out. It is simply its ionic weight in grams. So 1 gram ion of sulfate ions is 96 grams of sulfate ions. And the molar mass of sulfate ions is 96 grams per mole. So in this video, we tried to understand 4 different weights: atomic weight, molecular weight, formula weight, and ionic weight. And we tried to solve some very basic examples just to familiarize ourselves with the basic vocabulary of mole concept.